Hi girls, so this would be lesson 5 on coordinate geometry of the circle. Now there's a lot involved in this section, so I'm going to leave you have a few days to work through this and get back to you maybe Thursday. What was going to say, so this section is based on the equation of a tangent from a point outside a circle. Right, so up until now obviously we've been looking at, let me just go back. We've been looking at, say, lines intersecting circles, tangents to circles. If the line passes through the circle, it obviously has points of intersection, but a tangent to the circle would be a point or a line that touches off the circle at one point. So now what we're going to be looking at, I'll just go back, is... One second now. Okay, so what do we mean by tangents and touching circles, right? So a tangent, as we said already, is to a circle, touches a circle at one point and is perpendicular to the radius that joins the centre of the circle to the point of tangency. So the equation of a tangent to a point on a circle, how we would work that out, right? So if we were asked to work out the equation of the tangent to a point on a circle, the first thing we do is we'd find the slope of the radius that contains the point of contact. Okay, so that would be if you have a point on the line, the tangent, and you have the center, you can get the slope of that, can't you? As the tangent is perpendicular to the radius, you find the slope of the tangent. Okay, and then you find the equation of the tangent, right? So the first thing is find the slope of the line joining the center and a point that's on the tangent or the line. Get the perpendicular slope because the tangent is perpendicular to it, and then we'll be able to find the equation. So for example, find the equation of the tangent to the circle x squared plus y squared minus 2x plus 4y minus 20 is equal to 0 at the point minus 2, 2. Okay, so you could do a little sketch of this, right? And draw your sketch, find your center, find your radius, and put your point minus 2, 2 on the circle, because it will be on the circle because it's at that point there's a tangent. So we could find the slope of the radius, okay? So they work out, they just don't do it all the steps here, but get your center, which is 1 minus 2, and the point on the circle, which is minus 2, 2. So obviously the distance from 1 minus 2 to the circle, minus 2, 2, is actually the radius, right? So the slope of that radius is going to be using those 2 points as well. So we get minus 4 over 3. So that'd be the slope from the center to the point. Now we need to get the slope of the tangent, remember. So slope of the tangent, inverse, change the sign, is going to be 3 over 4. And we have a point. Remember, to find the equation of a tangent is a linear equation or a line. We just use the point minus 2, 2 and the slope 3 over 4. So plug it into your y minus y1 is equal to m bracket x minus x1, and we get the equation of the tangent to the circle at the point minus 2, 2 to be 3x minus 4y plus 14. Okay, so that's a good example to take down. I take down those points as well, step 1, step 2, step 3. Okay, the next part then is the equation. I think I started off with this and I shouldn't have started with this one, sorry. The equation of a tangent from a point outside of a circle. Okay, so the equation of a tangent from a point outside the circle. How would this work? Right, so the first step is you find the centre and the radius length of the circle. Grand, we kind of nearly always do that, so we can figure it out. We could draw a little sketch of it. We then let the slope of the tangent be m. Okay, because we don't know the slope of the tangent yet, right? So we're going to let it be m. Find the equation of the tangent using m as a slope, and remember that you will have a point on the tangent, okay? You write the equation in the form ax plus by plus c is equal to 0. It'll make more sense when we start doing it. And then find in terms of m the perpendicular distance from the tangent to the centre of the circle and set this equal to the radius length, and then you'll be able to solve for m. Rewrite the equation from step 3 using the value of m. So let's look at this one here. Find the equations, now equations it says, so there'll be 2 equations, of the tangents from the point 1, 0 to the circle x squared plus y squared minus 12x minus 10y plus 51 is equal to 0. Okay, So the first thing I would do is plot whatever I can, right? So they've plotted on an X and Y axis the point 1, 0, right? They've drawn their circle, right? A sketch, you can use your protractor or just do a sketch of it. You have your center. So they get the center to be 6, 5 using, your formula minus 2gx is equal to minus 12 and so on. 2gx is equal to minus 12x, 2fy is equal to minus 10 and minus g minus f. Okay, so remember, it doesn't say that the point now is on the circle, it's outside the circle. But those tangents, right, are passing through that. So we need to find the equation of those tangents, right? So what are we going to do, right? So we draw a little sketch. We have our two lines that are touching off the circle at one point. So the equation of the tangent is going to be y minus y1 is equal to m bracket x minus x1. Remember what we said is we'll find the equation of the tangent using m as the slope. We do have a point that's on each line, 1, 0. So as 1, 0 is a tangent, y minus 0 is equal to m bracket. So we get mx minus y minus m is equal to 0. Okay, so that's your equation in terms of m. Now, what else did we say? Okay, so this is the next slide. That we know that the perpendicular distance from that point to the line would be equal to the radius, wouldn't we? Because that's one of the facts that we know right now in as regards from the centre to a tangent of a circle, it forms a perpendicular distance or right angle. So we know that's right angle. So couldn't we work out the radius from our circle first of all using root g squared plus s squared minus c? We get that to be square root of 10. So now, isn't the perpendicular distance from the centre 6, 5 to the tangent, which is now in the form mx minus y minus m is equal to 0. The reason why we write it in this form is we always have the equation in the form ax plus by plus c. This is a coefficient of x. M is just like a constant, but here it's a coefficient of x. So that comes first. Y is just your other variable because it's ax plus by, and then m in this case is just a constant. We know that equals to the radius square root of 10. So now we'll be able to find m. So perpendicular distance, write down your formula first of all. You have your a to be m, you have your b to be minus 1, you have your c to be minus m. You have x1 to be 6, you have y1 to be 5. Fill that in and you know that it's going to equal to root 10. So just take your time, multiply it out, get rid of your modulus. Remember the modulus, you're always taking the positive value, you're squaring if you want to get rid of the square roots. And you're simplifying then that to a quadratic trinomial that you can easily solve. So I'd probably divide across by 5 then again, which they do here. A nice little quadratic trinomial. Do what you normally do your guided method, do your minus b, whatever you feel yourself. Get your factors, get your roots, and we get the two equations then, right? So as mx minus y minus m is equal to 0, just fill in m now. So for m to be equal to a third, now you could go back and do the whole thing where you're taking 1, 0 to be your point and your two slopes to be this and put it back into y minus y1 is equal to m bracket x minus x1. Yes, you could do that, but now you could just fill it into this because this is what we got the equation of the tangents to be on the original or in the previous page say. So fill it in. If you want, you can just multiply across by 3 to get rid of it. So we get x minus 3y minus 1 is equal to 0 to be one of the tangents. What do we say? M is, for the second one, m is equal to 3. So plug it into your mx minus y minus m is equal to 0, and that comes out to be 3x minus y minus 3 is equal to 0. So that's the other tangent then. Okay, so that's another example. I would definitely take that in that one. That's a really good example and it has come up similarly in questions before. Okay, so this is quite hard to see, but length of a tangent to a circle from a given point. That's kind of what we were doing there. So when dealing with problems involving tangents, it is important to remember that the line joining the centre of the circle to the point of tangency is the perpendicular distance to it, okay? So we will use this information to find the length of a tangent to a circle from a given point. This is illustrating the following example, right? So to find the length of the tangent, PT, so PT for the length of it, we'd have CP squared if you wanted, that's a right, like if you had this length, you could use your Pythagoras theorem, which you know from your junior cert trigonometry. CP squared is equal to PT squared plus CT squared, and then just manipulate the formula a little bit. So actually, like this example here, right? So it says find the length, If I zoom in a little bit. Find the length of the tangent from the point -5, 8 to the circle x squared plus y squared minus 4x minus 6y plus 3 is equal to 0. So let's go ahead, always get our centre, get our radius. Actually, is this the same? No, it's not. We're finding the length of the tangent, right? So the length of the tangent is different to the equation. Apologies, sorry. I just thought it was similar with root 10. Okay, so we know that this is root 10. Okay, and we're actually going to be able to work out now, because we have the centre and we have this point here, so we could work out the distance here, or the length here, using our distance formula. So we want to work out the length of this. So at the moment you only have 1 point on it, so we couldn't work out the length using our distance formula, but in fact this is CT. CP is going to be the distance formula from -5, 8 to 2, 3. Work out that. Now using Pythagoras theorem, this is a right angle. Remember, the side that's opposite the right angle is the hypotenuse. That's like your C squared. So PT squared, or C squared, is equal to A squared plus B squared. We're saying that PT squared is the hypotenuse side, is equal to CP squared minus CT squared. Fill in what you have. So you have CP squared, where we're squaring the square root, which is going to get rid of it, just to be 74. We're squaring the root 10, going to get rid of it, is equal to 64. PT squared is equal to is equal to 64. PT is equal to root 64, which is equal to 8. So therefore the length of this tangent, or the distance from P to T, is equal to 8 units. Okay, we don't know what it's measured in this case. So I have a few questions on the next slide here that I might get you to work on as questions for homework, but I'll come back and I'll reference that in my notes that I put up in Teams anyway, okay? Okay, so this is a worked example then taken from your book, and it's similar just with touching circles and tangents. So find the equations of the tangents to the circle x squared plus y squared plus 6x plus 2y minus 15 is equal to 0, which are parallel to the line 3x plus 4y plus 10 is equal to 0. Okay, so find the equations of the tangents to the circle that are parallel to this. So you know at this stage, the first thing we would do is we'd set up and we'd find our radius, and we'd find our centre using what we normally do, right? So the centre for this particular circle comes out to be -3, -1. The radius comes out to be 5, okay? You could do a little sketch of your circle then if you wanted to. The equation of any line parallel to 3x plus 4y plus 10 is equal to 0. You now know, don't you, that that's going to be of the form 3x plus 4y plus c. Okay, so therefore the tangents will have equations of the form 3x plus 4y plus c, and remember they're also parallel to 3x plus 4y plus 10. Okay, so what we can now figure out is that the perpendicular distance from the centre to each of the tangents equals the radius length of the circle. And we know that because it says that they're tangents to the circle. So obviously if they're tangents to the circle, they're also parallel, right? Or they're parallel to 3x plus 4y plus 10, but they're also, the distance from the centre to each one of those lines is always going to be equal to the radius. You know that once they touch off the circle at one point. Okay, they're not outside the circle, they're not inside the circle. So we can say that the perpendicular distance from -3, -1 to the tangents equals the radius length of the circle. So fill in, we have our A to be 3, we have our B to be 4, we have our C to be C. We have our x1 to be -3. We have our y1 to be -2. Fill it in, right? You know that that's now equal to your radius as well. Fill it in, right? You get the modulus to be c minus 13 over 5. Square both sides. Now they just take it as you're saying that this is equal to -25 or plus 25. Or else you'd square both sides. If you square both sides, remember this is not getting rid of the modulus sign. It's squaring it. So it'd be c minus 13 times c minus 13. You get your two values for c then to be c is equal to 38 and c is equal to -12, and you know that therefore the equations of the two lines that are parallel to 3x plus 4y plus 10 are now going to be filled into this, and you have your two values for c. So they become 3x plus 4y minus 12 and 3x plus 4y plus 38. Okay? Okay, so we have, I'm just going to zoom out there a little bit, sorry, lines and circles, so a common chord. So a common chord is basically like a line that passes through the circle at 2 points. Now, the diameter is actually an example of a chord, but in this case, it's not going to be, okay? So points of intersection of a line and a circle. So we use simultaneous equations to find the points of intersection of a line and a circle. If there are two solutions, then the line intersects the circle at 2 points, okay? So that's kind of what we come across already, that like, you know, when you have a line that's intersecting a circle, we use our simultaneous equations. But if there are two solutions in the line intersections at 2 points, that's that. If there's only one, it's a tangent. Okay, just a little recap on that. So actually, this example that I'd put up when I was originally preparing this PowerPoint, you actually don't really need to go back over, because I think you know this and you had a few questions on you had a few questions on this, say, basically in your previous exercise, right, which was based on like your simultaneous equations, right? So that worked out. I don't need to go back over that, okay? Now this one here, find the length of the intercept of the circle x squared plus y squared minus 10x plus 8y plus 16 is equal to 0 that it makes on the x-axis, okay? So if the circle intersects the x-axis at the points, isn't y always going to be 0? So that is literally just letting y equal 0 into this, right? So this is a chord, and it's just the way it's worded, I suppose, that it could kind of put you off. So find the length of the intercept the circle makes with the x-axis. So if it cuts the x-axis, y is always going to be 0. So if you substitute y into this, it brings you a lovely little quadratic trinomial, which you can easily solve and find that x equal to 8 and x equal to 2. So we get our two intercepts then to be 2, 0 and 8, 0. And they're the intercepts, but remember, it's also asking you to work out the length, okay? And the length is obviously the difference between 2 and 8 here, okay? And that's obviously going to be 6, isn't it? So 6 units. Okay, another example that I want to go through. So the common chord or common tangents of two circles. So say if we take, actually maybe it's better if I zoom in just like this. If we take two circles, so we've got circle 1 and circle 2, right? So S1 and S2. And say if we just subtract one from the other, right? So we would get 2x minus 6y minus 1 is equal to 0. This is the equation of the line which passes through the points of intersections of the two circles, okay? So if they intersect each other, it's like you're getting the simultaneous equations, you're cancelling what you can, you know, like you're getting rid of your x squares, your y squares, you're simplifying, and this is now equal to the equation of the line which passes through the points of intersection of the two circles. So it could be here or it could be here. So it's like the common chord. So if two circles intersect, then the line is the common chord of the two circles, okay? So if they intersect like this, the line is the common chord. If the two circles touch internally or externally, then the line is also the common tangent, right? So this is a common chord because I suppose it goes through the circle, and it goes through each circle, and it touches off 2 points here, okay? If they touch externally like this, the line that passes through here is a common tangent because it really is only touching off the two circles at one point. So let me just refer back to what I'm saying here, that if they touch or if they intersect, if two circles intersect, the line that passes through the 2 points of intersection is called the common chord. Whereas if they touch internally or externally, so this would be externally, then the line that passes through here is called the common tangent. So the points of intersection of two circles may be found by following the steps. So the points of intersection, this is how we'd work it out if we couldn't work it out any other way, like as in if we couldn't work it out like through simultaneous equations because they're both in that second degree form. The points of intersection of two circles may be found by following these steps. So find the equation of the common chord. Okay, so find the equation of the common chord. Excuse me. Find the points of intersection of that chord in any one of the circles. Okay? Any one of the circles will give it to you. So let's have a look at this example here. So it says, find the equation of the common chord of the two circles x squared plus y squared minus 6x plus 2y plus 4 is equal to 0, and x squared plus y squared plus 2x minus 4y minus 6 is equal to 0. So remember over here, the common chord of two circles, S1 is equal to 0 and S2 is equal to 0. So S1 minus S2 is equal to 0. That makes sense, right? So what they're saying, the first thing is you take one away from the other, okay? And like it's basically, it's not that it's taken, I suppose that it's like where you have one on top of the other, and you know the way when you're working out simultaneous equations, you take one away from the other, you change the signs. So that's what we're doing here. The common chord of two circles, S1 is equal to 0 and S2 is equal to 0. So we'd have S1 minus S2. So let's call this S1 circle 1, And let's call this S2 circle 2 and take that away. So we get the equation then to be 4x minus 3y minus 5 is equal to 0 is the required equation. So the points of intersection of the two circles, example 4 above, are found by solving equations 4x minus 3y minus 5 and x squared plus y squared minus 6x plus 2y plus 4 is equal. So for this particular example, it actually didn't do what I wanted it to do here. It actually only worked out the common chord. So now you know that will work out the common chord, right? But if you wanted to work out the points of intersection, as I said here, first of all, find the equation of the common chord, which they did here. And then they're telling you to take that common chord and take the circle. And basically, this is simultaneous equations where you have one linear, you have one non-linear. You write x in terms of y or y in terms of x and sub it into this, okay? So find the points of intersection of the chord in any one of the circles. You only need to use one of the circles then, okay? So you could try that maybe yourself. Okay, and finally then we have touching circles. Right, so we have circle 1. Actually, I'm going to zoom in here. So we've circle 1, or S, and we call it S1. And we've circle 2, we call it S2. We have center of circle 1 being C1 and we've radius 1, and center of circle 2 being C2 and radius 2. So they're circles that are touching externally. So if circles are touching externally, we can say that the distance from C1 and C2 is equal to R1 plus R2. Okay, so the distance from C1 to C2 is equal to the two radiuses added together. However, if we have two circles, so again, we call this S1 and S2, and we can see where the radius of S1 is and the center of S1 is, and we can see the radius of S2 and the center of S2. So if they touch externally, we can say that the distance between C1 and C2 would be the difference between the radius, so R1 minus R2. That's if they touch internally. So touching externally like this, and we could also get a common chord if we could put it across there. We get the distance between C1 and C2 to be the addition of R1 plus R2. And we'd have the difference, or if they touch internally, the distance between the two centers is equal to the difference between radius 1 and radius 2. Okay? So let's look at this question then. It says, prove that the circles x squared plus y squared minus 14x minus 6y plus 49 is equal to 0, and x squared plus y squared minus 6x minus 12y plus 41 is equal to 0 touch externally. Okay, so if they touch externally, this is the factors that we need to take into account. So let's work out our two centers. So let's put down this first of all. Let's work out the center for this. And you know what this stage how to work out the center. They don't have to do all the steps. You do all the steps out, but they don't do it for this example. Radius. Then we'll take the other circle, work out the center, work out the radius. Okay, now we need to use our knowledge of coordinate geometry of the line, and we need to get the distance between C1 and C2 using our distance form. That's equal to 5. So that should add up to the two radiuses together if they touch externally. And let's see, does it do? Does it do that? Sorry. Yes, it does. Okay. So as the distance from C1 to C2 is equal to the radius 1 plus radius 2, then the circles touch externally. So chords and circles. So we've already counted the very useful geometrical property of the circle, which states that the perpendicular distance from the center of a circle to a chord bisects the chord. So the perpendicular distance, now this would have been something that we would have come across in geometry. So the perpendicular distance from the center to the chord, it bisects it, right? It does because it goes from here to here. So in the given diagram here, let me zoom out. In the given diagram here, and I'll zoom into the diagram, D is the length of the perpendicular distance from the center O to the chord, and we can use Pythagoras theorem then to find D or P, okay? So it's like distance from here to here, we have a chord going across here. The length from here to here means the same. That's obviously because it's perpendicular. So it bisects the chord. So distance here and distance here is the same. But if you were to work out D, R, and P, if we have some of the lengths there, we'd be able to work out using Pythagoras theorem. Okay, so let's check out this example here. So a circle K has center 2, 4. Sorry, 4, 2. Sorry, don't know why I said 2, 4. and makes a chord of 6 units in length on the y-axis. Okay, so the chord of 6 units in length on the y-axis, right? We can see that, right? The chord passes through the circle at 2 points here. Find the equation of K. Okay, so find the equation of K. So we have this circle, the center for K, but we need to find the radius length. Now, we don't know the distance from here to here, right? But that would be the radius. Remember, any line that comes out from the center and touches off the circle is equal to the radius. So if the center is 4, 2, then the length of the perpendicular, BC, is going to be 4 units, okay? And how we got that, I suppose, is if you think of the length of the perpendicular BC is 4, is perpendicular from here to here is going to be 4 units, okay? So we get that obviously from using the center point here, right? And that we know that we don't know the radius length, but obviously we know the center. And we have the center to be 4, 2, so obviously that got from the x-axis, and the y is going to be 2 here, right? So if we know as well that the length of the chord is 6 units, right? So here to here, the perpendicular distance from the center to that line bisects it, okay? So that means that the lengths from here to here are halfway are the same length from here to here, and they're half of 6. So we can see here that AB is equal to half length of the chord. So the length of AB is actually 3 units here. So now using Pythagoras' theorem, couldn't we easily work out the radius length? And the radius length in this case is the hypotenuse. So that's your c squared is equal to a squared plus b squared, or ac squared is equal to 3 squared plus 4 squared. AC squared is equal to 25. AC is equal to 5. So the radius length is equal to 5. So we now have center HK. We have radius length 5, and you can plug it into your x minus h all in brackets c squared plus y minus k all in brackets c squared is equal to r squared. Okay, so that's another characteristic then to take in mind when we're talking about chords, is that we have that the perpendicular from the center of a circle to a chord, it bisects the chord. So bisecting it means it halves it then. So the distance from here to here would be the same as distance from here to here. Okay, so again, there's a few more questions on that page that I'll refer to maybe for you to work on as questions, for homework. We can see then from there, okay? So I'll think about maybe what questions to give you and get back to. But at the moment, you have a lot to work through. There's a lot of information that one, so you'll need a few days to kind of take your time going through it, okay?